Hello everyone, I hope you all are doing great. I welcome you all to this interesting series on system design. So in this video, we'll discuss about the client-server communication protocols and the connections. So basically here we'll see how the client and server makes the communication, what is TCP, what is TLS, what are the WebSockets, and what's the difference between REST, GraphQL and GRPC. So we'll make a deep dive on all these things. Basically we'll look how the communication is performed between the client and server, how the data moves between the client and server. Okay, so let's begin with that. So here first let's discuss a couple of terminologies before we deep dive. So the first one is the packet. So here the packet represents the chunks of data that is transferred between the client and server. So whatever the data that moves between the client and server, it is not sent as a single form or a single entity. It is sent in the form of packets that we can also call it as small chunks. Okay, so next what is port and the socket. So a port, you can say, is a door number in a big building. So in any server we'll have multiple ports over which the communication gets connected. So on that port we will be receiving all the data. So and when we call it as a socket, when we combine the port with the host name or the IP address or the host name of the machine, we call it as a socket. Okay, so the next one here we have is a handshake. So handshake is nothing but establishing the connection before sending any data. So the client and the server first has to establish a connection, and the process we will call it as a handshake. And once we have the handshake between the client and server, then the data transfer happens. Okay, the next one is the latency. That is the amount of time taken to transfer the packet between the client and the server. And the next one is bandwidth. Bandwidth is the data per second that can be sent between the client and server. So you can just take an example of the road connectivity, where if we have a single lane of a road, then the number of vehicles that can travel per second of time will be less when compared to when we have multi-lane roads, right? So that's the bandwidth. And the final one is a stateful and stateless. So with respect to stateless, the connection or the transfer of data in one connection has no relation with the transfer of data with the next connection. So they are completely stateless. But with stateful, here we mean that every time the client and server will be knowing about the previous requests. Okay, so we'll look into all these things in this video. So let's move to the next part. So here first let's get started with the TCP. What is TCP here? So TCP is the transmission control protocol. So where first it is the handshake, that is a connection that is done between the client and server. So during this handshake, there are multiple requests are sent. That is, we can call it as a three-way handshake and two-way teardown. Let's understand that with a simple example. Let me grab the screen annotator. Okay, so let's say we have this server and we have a client. So the client will send a synchronization message. It is like this. You can just imagine that this is a person 1 and person 2. The person 1 is sending a hi message. Now the person 2 will acknowledge to that hi, that saying that I have received your hi message. So now the server wants an acknowledgement from the client that whatever the hi message it has sent, it has received to it. So now it will send it back another hi message or an acknowledgement, you can say. So in this way there were 3 network connections happened to establish a TCP connection. Okay, so now this is when the connection is established. So now when they have to terminate the connection, again the same thing, the client will send a termination message and the server will respond to the termination. So that will be again 2 network calls. So total for a TCP connection there will be 5 network calls. So that's about the TCP connection. And once the TCP connection is established, then the packets are transferred. Okay, so next let's move. And the next is UDP. So UDP here stands for User Datagram Protocol. So it is different from TCP because here it is used for a purpose like where we need a very high speed data transfer, because it is a fire and forget kind of implementation, because here we don't have any handshakes and there is no ordering of the message. So here we may accept very high data transfer at the cost of losing some packets and losing the ordering. So we use TCP when we need the file downloads or the emails or the web browsing, basically when we want the data to be transferred in an order without losing in packet. And we use UDP when for the live streaming or for the online multiplayer gaming, where even some frames are lost, that will not affect the user experience. Okay, so that's the difference between TCP and UDP. The next one here we have is the TLS. So when our TCP connection is established, normally it will be it is not secured. I hope you have you have heard about the HTTP and HTTPS, right? So when a normal TCP connection is established, at that time only the protocol that is used to transfer the data, it is the HTTP. So your HTTP is hypertext transfer protocol. So that is we are defining a set of rules. On the basis of that rules, the data will be transferred between the client and server. Now, what if we want the data transfer to be secured? Because whatever the data that is transferred between client and server over TCP without HTTPS, that is without TLS, that can be easily decrypted, or that can be easily read in between if there is some hacker. Okay, because the network it transferred over the internet, and that is open. That's open network. Anyone can read it. So to make sure that the data is encrypted, we enable the HTTPS, that is we enable the TLS security. So now let's quickly understand how the TLS works here, because that's a very interesting thing to understand. So first here, let's say this is the client, and let's say this is the server and this is the client. So first the client will send a message to, once the TLS is established, so it will send a message saying that I want to transfer the data in a encrypted manner. Okay, so first message will be sent to the server. Now the server will respond back with its certificate. So it will be getting its TLS certificate from a certificate issuing authority. So it can be same or it can be different. So both the client and server will have its own certificate issuing authority. So it will be getting its certificate, and it will be sending that certificate to the client. So along with the certificate, the server and the client both will get a public and a private key. Okay, so along with the certificate, the server will send the public key. Okay, now even if there is some hacker sitting here, he will be able to read this public key and the certificate. Okay, but still that's of no use to the hacker. Why? We'll just understand that. So once the client has the certificate and the public key, it will first verify that certificate with its issuing authority. Once the certificate is verified, it will generate a session key. Okay, a session key will be generated by the client, and it will encrypt that session key with the public key which the server has sent in the last request. Okay, now this encrypted session key will be sent back to the server. Okay, now here you may have a question that the hacker can hack this key, the session key, and it will decrypt it back. But the catch here is that the session key that was encrypted using the public key, that cannot be decrypted using the public key itself. It can be only decrypted using the private key that is only present with the server. So that's the catch. And due to that, now the hacker cannot be able to hack that session key. So hacker has no role over here now. So now the server has the session key that is encrypted, so it will decrypt it with the private key which it has. And now both the client and the server have the same session key. Now once this TLS connection is established, post that, now whatever the data that will be transferred in between, that will be encrypted with that session key, encrypted and decrypted with that single session key which is present with both client and server. So that session key is now is with nobody else except client and server. And due to that, whatever the data that will be transferred between both of them is completely secured. So that's the reason it is always recommended to trust only those websites or the servers that has enabled the TLS security. Okay, I hope you are able to understand this. Let's move to the next slide. Okay, so the next slide we have regarding HTTP. So we already discussed about the HTTP. So here HTTP is a protocol that is agreed between the client and server to transfer the data in a certain format. Okay, so let's look at the evolution of HTTP here. We started with HTTP 1.0 where we needed to have a new TCP connection for every file transfer. Okay, but now that was overcome with HTTP 1.1 where they introduced the keep alive header. So when the server looks that there is a keep alive header in the request, then it will maintain a persistent connection with the client until it is terminated. And during that, if there were multiple files, then they were all transferred in that one single TCP connection. But the drawback here was, let's say if we have 3 files, then all the 3 files need to be sent in a queue, like they cannot be sent parallelly to the client. So that was a drawback, but we overcome the multiple TCP connections. So in the next version, that is HTTP 2, we introduced the multiplexing where now with a single TCP connection, the multiple files could be transferred parallelly, okay, instead of queuing them. And then finally, in the latest HTTP 3, it was completely we completely replaced TCP with a new protocol, that is QUIC. Here it's quick UDP internet connection. So that stands for QUIC. So here there is only one handshake to make the connection, and it is as fast as UDP. Okay. So it's the combination of TCP and UDP, where it gets the feature of handshake from TCP, and also maintains the order of the packets, and also it gets the faster processing of these packets from the UDP. Okay, so that's the latest protocol. Okay, so let's move to the next slide here. That is regarding the persistent connection and keep alive. So that we just discussed using the header keep alive. Why that is important? Because if we try to make a new TCP connection every time, then we needed to first do a DNS lookup, then TCP handshake, then again there will be multiple network calls for TCP handshake, and finally actual HTTP request. So it would have costed us 100 to 300 milliseconds for every TCP connection. So with keep alive solution, we are keeping the connection alive, and the TCP socket stays open. Next request skips step 1 to 3 entirely. So that would complete in the 5 millisecond totally. So that is the difference with the keep alive. And the next protocol we have is the WebSockets. So here the problem with the TCP or the UDP is that it cannot be started or established from the server to the client. It always has to be established from client to the server. Okay, so in some cases where we explicitly want to send some data or a connection request from server to the client, we don't have any option. So this is where WebSockets comes into picture, where we can create a persistent connections between the client and server, and when that is created, even the server can send the data to the client whenever it is needed. Okay, so we can see that in case of chat applications. So for example, okay, so how the WebSocket works, it's a very simple mechanism. So for example, if this is the server, let's say if that is the client, and if this is the server, and this is another client. Let's say these are nothing but the users. This is the user 1, okay, and this is the user 2. They both wants to make a chat communication. So now how that is enabled using WebSockets. So first they will establish a WebSocket connection with the server. Okay, both the users will be establishing a WebSocket connection with the server, and now whatever the message that will be sent by the user 1, that will be first sent to the server. So the message will come here, and the server will be maintaining the persistent WebSocket connection with the user 2, where the message has to be transferred. So it will automatically pass that message to the user 2. So that is possible with the help of WebSocket connections. So the same thing, when the user 2 will reply, it will come back to the server, and it will then pass back to the user 1. So that is the reason here we needed to use WebSockets, where the server can make a call to the client whenever it is needed. So this is one of the use case where WebSockets are extensively used, that is the chat applications, and any kind of live applications we see the WebSockets being used there. For example, in the live cricket score application, where we automatically start to get the live score once the match starts. We don't need to refresh the page or something like that. So that's again done using WebSockets. So these are the two examples that where we can see the WebSockets implemented. Okay, so next, moving ahead, we have the REST. So here REST stands for representational state transfer. So till now we discussed that how the data will be traveling between client and server. Now we'll discuss or see how the data needs to be structured so that we get a proper response. So with REST, here it stands for representational state transfer. So to understand this, you can take an example of restaurant where when we go and if we want to order a burger, then in the menu we'll see that usually they will mention as the size, like small, big, or small, medium, or big, right? So here let's say if I order a medium burger, then from my end I cannot decide the size of that, right? If I order a medium, then the owner of the restaurant will serve me a medium size of burger which they have already decided. Like, so that's exactly how this REST works. So here we just need to make a request for a particular data, like it can be a GET request, POST, or PUT request, and according to the server's configuration, how we are configured in the code, according to that we'll get back the response. For example, if I ask for a user profile with an user ID, when I send a user ID, it will return me all the data that are present in that user JSON object, okay, having user ID, name, email, phone number, and everything. I cannot like skip the phone number and email and I just get the user ID and name. No, that cannot be possible with the REST, right? So for that we need to create a separate object. There is no control on the client side regarding what will be the structure of the data that the client will be receiving for a particular request. Okay, so that's the REST here. The pros are like standard and predictable data response we'll get from the server. It is stateless, that is one request doesn't have any relation with the next request, and it is very easy to cache because we know the structure, it is well defined, and every developer knows it. That's because it's widely used in most of the enterprise applications. What are the cons here? Sometimes it's overfetching, as we discussed. Let's say if I just need the username and pass or the email, but the JSON object will contains other data as well, and it's sometimes underfetching, need separate request for just user plus orders. Okay, so that's the REST, that is representational state transfer. Next we have the GraphQL and gRPC. So GraphQL is developed by Facebook. So here again taking the same example of burger. So with GraphQL, if I say a medium sized burger, then here I can decide what should be the size of that medium, that I can define it, and I can also customize that burger. So exactly like that, with the GraphQL, the client gets an authority or a liberty to decide what data the client needs from the server. So the custom built burger form where tell the chef exactly what kind of burger we need. A single post request to the GraphQL query specifies exact field that are needed, and no over or under fetching happens here because we know exactly as a client what data we need from the server. So great for mobile bandwidth. Okay, but it is harder to cache because caching is done when we already know what data is frequently accessed, but here it is not the case, and the complex queries can overload the server. So it depends on the use case where it is needed. It can be used when we need certain set of only certain set of data from the server. We'll look into the a quick demo of all these things in the coming section. And next we have gRPC. So here gRPC stands for Google Remote Procedure Call. So gRPC is basically used between the microservices communication, that is service to service communication, because of very low latency and faster or you can say faster data transfer. So in gRPC, like unlike the normal REST request and response, here the data is transferred in a binary format, and because of that the payload size become very less, and the latency becomes very low. Because of that the processing becomes very fast. Okay, so that's regarding gRPC. We'll look into that a demo very shortly. So in gRPC, the data transferred is a binary data over HTTP2. So the call server functions like a local function. So it is like calling a local function, but it happens over the network. And extremely fast serialization and deserialization, strongly typed, and it is done over HTTP2. Okay, so what are the cons here? No browser friendly without the adapter. So because it mostly can not use between client and server. It is only used between server to server. Okay, not human readable in network tabs. Okay, so that's add another layer of security. So that's regarding the GraphQL and gRPC. So here visualizing the real world flows, how everything comes together in production. For example, first of all, when we make a call to the backend, when any client make the call to the backend, first the DNS is resolved, right? Because let's say if I make youtube.com, if I just add it over here in the browser, then that YouTube domain name has to resolve to some IP address. So that's the DNS resolver. Once the DNS is resolved, a TCP connection with the TLS handshake is done, which we already discussed. Once that is done, it will request the data from the server. So it will get that data over the HTTP protocol, and that's how the connection is established between the client and server, and data is transferred. So the role of application load balancer in microservices. So in millions of mobile clients connect via unpredictable networks. So load balancer terminates all the complex TCP and TLS connections. Load balancer talks to the backend via pre-established keep alive connection pool, and it will backends never pay the TCP TLS handshake tags and maximum throughput. Okay, so it happens only till the backend, till the load balancer, and down to the load balancer it can happen with HTTP as well, because it's an internal network. Okay, so that's how it is implemented in the production microservices architecture. But it's not the only way that it is done. If it is a very highly secured application like banking application, then the architecture may change. Okay, so next we have the performance and trade-offs, a decision table. So here for different kind of applications or use cases, these are the different protocols or the tech that can be used, like for live gaming or Zoom call, UDP that we already discussed. Like fetching a web page, we can use HTTP, HTTP 2 or 3. For chat application, we can go with WebSockets. Then for mobile apps, we can go with GraphQL, or for microservice to microservice communication, we can go with GRPC. So we'll look into all of these in a demo after discussing this. So next, finally, these are the takeaways that we already discussed in this video. Okay, so let's look at a quick demo. Okay, so let's look at the demos. So I have already created the demos on the code related to that. So here I will just run those demos and I will show to you, and we'll discuss what is happening for every scenario. And regarding the code, I will be sharing that over the GitHub, so you can look into that. Okay, so let's first start with the TCP handshake demo. So you'll understand how the TCP handshake happens between the client and server communication. So let me jump into the TCP handshake demo directory, demo1 TCP shake. Okay, so here if I look, I have these files. So first I need to start the Docker containers. So those Docker containers will help us to run this demo. So for that I need to run the Docker compose file. Before that I need to start the Docker desktop on this Mac. So let me just start it. Okay, so the Docker desktop is running now. Let me come back here and now let me run this demo. So before that we need to run the Docker compose YAML file that will create the required containers, and I'll just show you after that. So for that let me just run this command, Docker compose build in a detached mode. Okay, so the containers are created. Let's look at here. So we have a one single container. Okay, so now let me run the demo file, that is bash run demo.sh. Okay, so now here we can see in the logs what is happening. So this demo is created in a way where it will make a client and server call, and during that call we will see what are the logs printed. So here in the beginning, what are the logs you are seeing here? These are the actual logs that you will see in every client and server communication. You can just look at them in the network tab in the browser console. So we will be seeing the similar logs. So what these logs mean, let's try to understand that. So first it's a message, that is the synchronization message sent by the client to the server saying that I want to connect, and then the server will respond back saying that I have acknowledged your synchronization message, and now we need an acknowledgement from the client saying that it has received the client server's message. So that is the reason the third one is an acknowledgement from the client to the server. So these are the three network calls are happening to establish the connection. So once the connection has been established, then the data is transferred, and then finally the connection is teared down. So that the final connection tear down also has two network calls, both of them agreeing to terminate the connection. So here these are the 5 network calls are happening for one TCP connection. So that's the reason TCP connection are very expensive, and we should optimize, or we should always design the system in a way where we need to have as less possible as the TCP connections between the client and server. Okay, so that's the first demo. Next, let's move to the next one. So the next demo here we have is the TCP versus UDP. So here we'll be trying to simulate the TCP and UDP servers with the Python code. Here it is not actually the UDP server or UDP data transfer, but with the help of code we are trying to simulate it just to understand the behavior and the difference between TCP and UDP. So let me go into that, demo 2 TCP versus UDP. Okay, so here also we need to first run the docker compose.yaml file that will create the required containers, and then we can begin with the demo. So for that let me run this docker command, that is docker compose build the docker containers in a detached mode. Okay, so our containers are ready. So if we look at them, these are the two containers. One is TCP UDP server and TCP UDP client. So these two will help us to complete this demo. So for that now let me run the run demo.sh file. So for that it's a bash file. So bash run demo.sh. Okay, so here you can see we are trying to simulate the TCP and UDP data transfer. So with TCP we are sending 1000 packets, that is finished in less than a second, like just a fraction of a second, and TCP guarantees all 1000 packets arrive retransmits if any lost, and then we are sending the 1000 packets with 30% simulated network loss that we expect in the UDP, and that finishes more faster than the TCP. Okay, so here 320 of the 1000 packets were lost. So finally with the UDP only 680 packets were received. So final comparison, TCP is a bit slower, but it has guaranteed that all the 1000 packets were delivered. But UDP was faster, but it was not reliable in terms of the packets or the data that is transferred. Okay, again we are doing a simulation around 2. We could see the similar behavior where in the round 2 also UDP lost couple of packets. Okay, so that's the core difference between the UDP and TCP, where TCP will guarantees us with the transfer of all the data, all the packets, but at a cost of the network. Like there will be some lag compared to the UDP. Okay, so that's regarding the second demo regarding the TCP versus UDP. Next, let's look at the third demo. So demo 3, TLS handshake. Okay, so here we don't need to run any Docker containers. We can just simply, I can run this bash file, run demo.sh. Okay, so here let's understand, as we already discussed regarding how the TLS connection is established between the client and server. So that's what here we are simulating. So here we are acting as a client and we're trying to connect with the google.com, and that's an HTTPS, because 443 is the default port of the HTTPS and 80 is the default port of the HTTP. Okay, so when we want to upgrade to SSL, that is TLS, it will automatically upgrade to 443. So every TLS message, watch for this. So let's see here what's happening. So when we as a client will send a request to the server, it will, as already discussed, the server will send back its certificate along with algorithm that will be used to encrypt the session keys. Okay, so it's the client hello, then the server will send back a hello, then the certificates are exchanged, and finally the server key is exchanged and then finished. And now using that final session key, all the data will be encrypted and decrypted between the client and server, and that session key is now only present with the client and server, so there is no chance of data getting hacked between the client and server when it is transferred over HTTPS. Okay, so this is how the certificate will look like, and here who has issuer, who is the issuer, and what's the expiry of the certificate. These are the details. So what did we just saw? First the client said hello, your machine proposed the ciphers, that's the encryption keys. Then the server sent an hello, that is Google chose TLS. So this is the encryption key or the encryption mechanism that is chosen by the server, and it also sent the certificate. Google proved its identity, then key exchange happened, and all the data after that at this point is encrypted. Okay, so that's a high level simulation of the TLS, but in detail we have already discussed while discussing the initial explanation. Okay, so let's next move to the next demo, that is HTTP 1 versus HTTP 2. Let's see what's the difference here. So for that, let me just run the demo 4. So demo 4, HTTP 1 versus HTTP 2. So for that, again I need to run the Docker containers. So let me run that. Okay, so it has just created 2 containers for the HTTP 1 and HTTP 2 server. So here we'll see what's the difference. Okay, so before we start this demo of the difference between HTTP 1 versus HTTP 2, we need to configure a couple of things. So for that, let me go to this. What are the steps? So first we need to run the bash generate certs.sh file. So this is going to generate the certificates, because certificates are needed for HTTP 2. So browser will not able to make a communication without having the certs, because HTTP 2 mandates using the TLS communication. Okay, so for that we need to first generate it. So certs are generated, and then we will generate a couple of dummy images that will help us to run this demo. We'll try to implement, or we'll try to get the images from the server using both HTTP 1 and HTTP 2, and we'll see the difference. Okay, so we have the images. Now let me run the Docker Compose. So we have already run the Docker Compose build. So we have already running both the HTTP and HTTP 1 server and HTTP 2 server. Okay, So now let me go to this URL. Okay, so here we are doing the image loading test. So if I go to the inspector window and go to the network tab, and if I reload this, you will see how HTTP 1 is performing. So we can see a waterfall mechanism where it is pulling the images one by one in a queue manner, in a sequential manner. So in HTTP 2, images load in parallelly. So let me run the HTTP 2 here, HTTP 2, and that should be running on HTTPS. So here, as the certificates are generated by us, and we are running on the local host, so there is no authority that will like validate for the local host. So because of that, we are getting this warning message. So here we'll go to advanced, and we can just proceed to the local host. Okay, so here if you go to inspect and check, and let me reload this, so you'll see here it's not a waterfall mechanism, it's all getting done in a parallel mode. All the images are pulled in a parallel mode. Okay, and the time took is 0.13 seconds, and here it's 0.14 seconds. So with the parallel pulling of the images, we see there is a lesser time involved, but when we are doing it over HTTP 1, we are having it's taking a bit more time. Okay, so that's the difference between HTTP 1 and HTTP 2. Okay, so let's look at the next demo, that is regarding the keep alive performance. So here we'll run this Docker compose file that will create 2 Docker containers. That will be, one will act as a client and another will act as server. And then we will run the next Docker command that will make the set of request from the client to the server container. Okay, so here the request will be made in 2 sets. The first set of 100 requests will be a normal, using normal TCP connections. That is, every request will establish a fresh TCP connection. Okay, but the next set of 100 requests, in that there will be only one TCP connection established, and with the help of keep alive header, it will like perform the other 99 requests. Okay, so then we'll see which sets will take less amount of time, and we'll see the difference in the performance. Okay, so for that, let me first run this command that will create 2 Docker containers. One will be keep alive client and another will be the keep alive server. Okay, now let me run this. That is going to trigger those requests, and we'll see the logs. Okay, so here you can see first 100 requests, the connection will close a new TCP connection per request. So we made 100 requests, it took 0.046 seconds. Next connection, with the help of keep alive, reusing the single connection, 100 requests were made and it took 0.040 seconds. So it was 1.2x faster. That saved this amount of time. So that we are seeing a very significantly less difference, because both the containers are on my own machine. There is no latency, there is very fraction of latency, we can say. Because of that, we are seeing a very small difference, but in a real production systems, this will have a major performance difference. Okay, now let's look into the next demo, that is the WebSockets. So for that, let me get into the WebSockets directory, cd demo 6 WebSockets, WebSocket chat. Okay, so now here again we need to run the Docker containers. So for that, let me just quickly run the containers, and that will create a Docker container, and then we'll, using the client, using the browser, we'll establish the WebSocket connection. Okay, so if we look at here, we already have the WebSocket server and WebSocket web. Okay, so now if we hit this, so it is, we are hitting the WebSocket web. Okay, and that will connect to the WebSocket server. So if we hit that, and then we'll check the let me just hit it over here. So here the WebSocket demo is running, and if you look, initially the WebSocket connection was a simple TCP connection that was done to this WebSocket server. But as soon as it saw that it is an WebSocket connection, the normal TCP connection was upgraded to a WebSocket one. Okay, so now this is the WebSocket localhost 8765. Initially it was a normal HTTP connection, so the protocol got changed to WebSocket. So now over this, the data will be exchanged between the client and server. So here if I just run it in multiple tabs, you can see that Now if I just make a chat, you will see that the chat get reciprocated over here as well. So if I'll change the name to John, right? I'll just say, hey Jack. Okay, so now this will also be read over here, and here let's say we'll change this to Jack, and let's say hey John. So you'll see this message will be present over here. So how we are able to get the message back into another tab, that is because of the WebSocket that has been established between the client and server. So one client, that is the one user, is sending the message that is getting passed to the server. Now the other user has also established a WebSocket connection with the same server. So because of that, now the server is broadcasting or sending back that message to all the users that are connected over the same WebSocket. So that's the reason when this user is sending any message, it is getting read by the other users as well, because both of them are connected on the same server through the WebSocket. Okay, so that's the concept of WebSocket and a simple demo for that. Next, let's move to the next one, that is a difference between the REST and GraphQL. Okay, so for that, let me get into that directory. CD demo 7 REST versus GraphQL. Okay, so here also I need to first run the Docker containers. So this will help us to understand the data flow between the client and server. So with the REST, as we already discussed, we need to the state is already defined. If we ask for some data, it is going to be in the same state. But with the help of GraphQL, we can define a state or like which state data we need from the server. So we'll see a quick demo of that. So the containers are running here, REST versus GraphQL. Now let me just go to this. I think it is 5001. Okay, I'll just update it over here as well, because 5000 is already reserved for some other server on the Mac machine. Okay, fine. Now here we have these two differences. First, let me just click on this. So that will fetch the result for the user 1 and then for the orders. So if we do this, you can see that for the user 1 details, we needed to send this first request, and for the user order details, we needed to send another request. Okay, so total response size was 365 bytes. So we needed to make two different calls for the same user details. But now if I go over here, you can see that within the same one request, we could have got all the details that were needed for that user. So here for user, we just needed the email, ID and name. Okay, but and the order details. We don't need the other details here. But here in this case, that is not possible. If I want to get the user details, then it will give me all the details that are stored for that user entity in the database. Okay, otherwise I need to add a customized, or I need to write a customized code that will going to return this. Okay, but then again that doesn't solve our purpose. But here that is solved using with the help of GraphQL. Okay, so that's the difference between the REST and GraphQL. So next, let's move to the next demo. That is the difference or the comparison between GRPC and versus REST. So we already know the REST is basically used between the client and server, and the data is mostly transferred in the form of JSON. But GRPC is basically used between the service to service, or between the microservices, and here the data is transferred in the form of the bytes. Okay, so here let's run this demo and let's see. So let me just get into demo 8, GRPC versus REST. Okay, so for that, here again, let me run the Docker containers needed for this demo. Okay, we can see that we have these three servers. So one is GRPC server and REST server, and we have this another server, that is GRPC benchmark. So this server we have configured to make the calls, that is so here it will make the calls 5000 requests to each server and prints the comparison. So if we go inside this, we will already have the logs. So that's GRPC versus REST 5000 requests. So sending 5000 requests in the form of JSON data or HTTP1. So it took 2.213 seconds, and then we made again 5000 requests using protobuf, that is using the binary serialization of the data. and it just took 1.4 seconds. So gRPC was 1.6x faster than REST. Why? Because protobuf binary is smaller than JSON text, and no JSON parse or stringify over it. That is, there will be parsing of JSON data between the client and server, but that is not the case here. And HTTP2 multiplexing versus HTTP 1.1 sequential, that we already just seen a couple of time back. So connection reuse is inbuilt in the gRPC channels. So these are the couple of reasons why gRPC is much faster than the REST. Okay, so that's all we needed to look into the demos here in this video. So let's catch up in the next video.